Guys, it's finally time to build confidence intervals. So the goal of a confidence interval is to estimate the size or the magnitude. How small or how large might a particular population parameter be? So if we go back to the class bead bag example, let's say we want to estimate the proportion of red beads in the bag, where P is the population proportion of red beads in the bead bag. So to estimate the magnitude of this parameter, we should use a sample proportion, or a p hat, that's based on a simple random sample, or an SRS. So we should use a sample proportion based on a simple random sample from the bag, since that p hat, that sample proportion, is an unbiased estimator of the real parameter p. So let's say that in an SRS, we obtain 9 red and 16 white beads. So that's our data. So this means that the sample size in total, 9 plus 16 makes 25. So this is just like the samples that we were using in class. And the sample proportion, the p hat, is 9 red out of 25. And that turns into a statistic of 0.36. This 0.36 is called the point estimate. And it's our best guess at what the population parameter, at what p really is. But understand, if we take another simple random sample and create another p hat, we may get a different value. And that's because p hat, the sample proportion, is a random variable. But because it's a random variable, we can use its sampling distribution to describe how far above or below the true parameter, p, this point estimate will tend to be. So the sampling distribution of p hat and the conditions that you have to check are as follows. So this is review. P hat is distributed approximately . It is approximately normal. The true population parameter is at the mean, and then the standard deviation is found by taking the parameter times 1 minus the parameter, so the real probabilities of success and failure, and dividing by the sample size. So that's how we distribute p hat in general. So randomness, we would like to have a simple random sample. We at least need a random sample. So for randomness, we want a simple random sample. Or at the very least, we would want a random sample. So for independence, I need to know by the 10% rule that 10 times n is less than or equal to the population size, the population from which we are sampling, and then this is about proportions. So for normality, I need to take n times p, that should be greater than or equal to 10, and that's the success count, and the failure count of n times 1 minus p, that should also be greater than or equal to 10. Those are our conditions. Now, notice there's a little snag here. So in practice, when you build a confidence interval, you don't know the real population parameters, or you don't know the real population proportion here. So we're going to have to replace it with the point estimate, p hat, when we build the standard deviation. So this means that instead of calculating the square root of p times 1 minus p over n, what we're going to have to do is build something different. We're going to have to build what's known as the standard error. And it's the same formula, But in the place rather of p, we're going to have to use our best guess for p, and that's p hat, the sample proportion. So instead of p, we have to use p hat times 1 minus p hat, and we'll divide that by the square root of the sample size. This is called the standard error. So through the variability that's a natural part of random sampling, if many random samples are taken, so remember, within one standard deviation, so about 68% of the time, the true parameter will be within one standard deviation of the point estimate, p hat, and that's due to the approximately normal shape. So this lets us build a very, very simple confidence interval. Here, take a look at the second page. So by adding the standard error to and subtracting the standard error from 0.36, we can create a very basic first step at a confidence interval. So here is the point estimate. We have to calculate then the standard error. So the standard error is going to be the following. It is the square root of our point estimate. So that's 0.36 times 1 minus the point estimate, which is 0.64. And then we need to divide by the we need to divide by the sample size, which is 25. So our standard error is 0.096. So I'm going to take the 0.36 and I'm going to subtract 0.096. And then I'm also going to add 0.096. And those are going to give me the lower and the upper boundaries of our confidence interval. So 0.36, our point estimate, minus 0.096, and then 0.36 plus our standard error. So that gives us 0.264, I'm writing those down, and 0.456. So often we write a confidence interval in parentheses like this. Don't confuse it with an ordered pair. It is not an ordered pair. This is the lower boundary, and this is the upper boundary of our confidence interval. So the method used to create this interval right here, it will capture the true parameter in about 68% of intervals created from simple random samples when this procedure is repeated many, many times. So we would interpret this as a 68% confidence interval. So just like we saw in our study guide, we are 68% confident that and again, our confidence intervals will be about a parameter, so you need to describe what it is. It's the proportion of red beads in the bead bag, so you should describe it that way in context, is between the lower boundary of 0.264 and the upper boundary of 0.456. So this percentage here, that's the confidence level, and the confidence level describes the accuracy of the method used if repeated sampling is performed. If we took simple random samples of size 25 and repeatedly found the standard error and repeatedly went one standard error below and above that point estimate, we would create a bunch of 68% confidence intervals. That's the accuracy level of this method if we repeated this process many times. So notice at 68%, this method isn't particularly accurate. So we can increase the accuracy level of the method by creating a new method, by increasing the number of standard errors that we add to and we subtract from the point estimate. So this number of standard errors, that's known as the critical value, or Z star. So this time, let's build another confidence interval using a Z star of 1.5. So literally what that means is we're going to add and subtract 1.5 of our standard errors, which is 0.096, we're going to add and subtract 1.5 of these standard errors to and from the point estimate of 0.36. So 1.5 times 0.096 that comes out to be 0.144. So this 0.144 has a special name that we're going to talk about in just a second, but I'm going to add the 0.144 to the 0.36, and I'm going to subtract the 0.144 from that 0.36 and create our new confidence interval. So there's the point estimate minus 0.144, and here's the point estimate plus the 0.144. So these are the new boundaries of our confidence interval. So the lower boundary is 0.216 and the upper boundary is 0.504. So let's go back to the lesson here. There we go, lower boundary and upper boundary. So this confidence interval, though, has a different level of confidence because I've used a different number of standard errors in order to create the lower boundary and the upper boundary. So we need to decide. What level of confidence is this? So what percentage then of approximately normally distributed data will be within 1.5 standard deviations above and below the mean? So this is a question that we've answered many times. We can use the normal CDF command, and we can simply find the percentage of data between negative and positive 1.5. That percentage will tell me the level of confidence that we've established in this confidence interval. So I'm going to use the normal CDF command. This is something where if you wanted to, you could use the shade norm command if you wanted to. So you might be asking yourself, where did the 1.5 come from? I just chose it. I chose the Z star to be 1.5 just to have another example. So negative 1.5, positive 1.5. I want to find the percentage of approximately normally distributed data that will be in between those two Z scores, and it's about 87%. So this is about 0.87. So what this means is that we have created an 87% confidence interval. So the combination of Z star, so in the above example we used 1.5, and the standard error, our standard error was 0.096 in this above example. This is called the margin of error. So the margin of error is plus or minus the critical value, which is just a specific number of standard errors that we are going to use above and below the point estimate in order to make our confidence interval. And we get to choose that Z star depending on the level of confidence that we want for our confidence interval. So we can choose a level of confidence, choose a confidence level. And that will determine Z star. That will determine the critical value. And of course, the p hat, that comes from our sample, our random sample from our population. That's the point estimate, the sample proportion. And then n also comes from the sample. That's the number of observations that we randomly selected from the population. So the critical value and the sample size, here's the critical value and the sample size, they determine together the margin of error. So more confidence, that's desirable, but this results in a larger critical value, and what that will do is make a bigger margin of error. So we will be adding and subtracting a larger number of standard errors from the point estimate. That will end up in a wider interval. Again, more confidence, that's desirable, but that ends up with a wider interval. So notice we can counteract this by increasing the sample size, by using a larger sample size that's in the denominator of the standard error. So that will reduce the standard error, and that will make the margin of error smaller, and that will make for a smaller confidence interval. In applied research, a confidence level of 90% or higher, those are considered very desirable. Those are the ones that tend to get published in professional literature. So let's build and interpret a 90% confidence interval for the proportion of red beads in the class bead bag. So notice, to find the critical value, to find Z star, we need to determine how many standard deviations above and below the mean will capture the middle 90% of an approximately normal distribution. So let's go take a look at the next figure. So this figure will help us understand this math. So what I want to do is take an approximately normal distribution, and I want to center or capture the middle 90%. So the area of this shaded part here is 0.9, and I need to find the z-scores. This is a symmetric distribution, so they will be opposites. There's a lower and an upper one. They will be opposites. I need to figure those out. So if the shaded area above represents the middle 90% of the standard normal distribution, so that's a normal distribution with a mean of 0 and a standard deviation of 1. What this means, if we've kept the middle 90%, what this means is 10% of the distribution has been cut off from the outer tails here. So, or notice, 5%, half of the 10%, 5% has been cut off of each side. So that's by the symmetry of the normal distribution. And the key is to use that 5%. So this lower boundary right here, I can find that by using the inverse norm command. So I can think of this lower area right here as a percentile. So to find this z-score right here, I can use the inverse norm command, put in the percentile of 0.05. So on the calculator, to get to the inverse norm command, that is second variables. There's the inverse norm command. So I will put in 0.05. Don't change the mean and the standard deviation. So this comes up to be negative 1.648. I'm going to round that to negative 1.645. So this lower z-score is negative 1.645. The upper one is positive 1.645. So what we have found here, in this way, we've determined that z star, the critical value, in other words, the number of standard errors that I need to use in order to calculate my margin of error, is 1.645. And that will give me 90% confidence, and now we can build our 90% confidence interval. So here's our example. Build and interpret a 90% confidence interval for the proportion of red beads in the bead bag from a simple random sample where that sample had 23 red beads and 27 white beads. So first we need to check the conditions. These conditions will allow us to build our confidence interval because these verify that the sampling distribution that we've studied for sample proportions is appropriate or is usable here. So we need a random sample, and I can see that we have used a simple random sample. It would be fine to just say that we have used an SRS. That abbreviation is acceptable. So for independence, notice I need the total sample size. So the 23 and the 27, those are, if you will, the counts of successes and failures, the red and the white beads. But if you add that together, you can see the sample size is 23 plus 27. So the sample size is 50. So no problem for independence. 10 times 50, that's 500. and that is less than or equal to the number of beads in the bag because there were 1,000. There are 1,000 beads in the bag. So for normality then, we are going to act like we don't remember. We are going to act like we don't remember what the real parameter is. So when you build in practice a confidence interval, you don't know what the real parameter is. So something to think about here. The normality condition has to be checked not by using p because you won't know p. You're trying to use your confidence interval to capture the true population parameter, to decide what is its magnitude, what's the size of that population parameter. So the normality condition also has to be checked with the sample proportion, with the point estimate. So I want n times p hat to be greater than or equal to 10, and I also want n times 1 minus p hat. I want both of those to be greater than or equal to 10, so maybe we should find our point estimate first. So our point estimate is the 23 red beads out of a total sample size of 50. So that point estimate is 0.46. So the critical value that we are going to use, we want to build a 90% confidence interval. So we already found previously the critical value that we want to use is 1.645. So let's not forget to go back and check this condition here. So my sample size is 50. So 50 times 0.46, 50 times 0.46 is 23. That's greater than or equal to 10. And the number of failures. So in this case, that would be 50 times 0.54. So that's the failure count in this context. That's the number of white beads. That's 27. And that's also greater than or equal to 10. So our conditions are easily met. And we're ready to calculate then our standard error. So the standard error is using the same formula for the standard deviation of the sampling distribution that we used in the past, but I don't know p, so I am stuck using my best guess for p, which is p hat. So that p hat is 0.46. So I have to take p hat times 1 minus p hat and divide by the sample size of 50. So that will give me the standard error. So that's the square root of 0.46 times 0.54 divided by 50. So this gives me a standard error of pretty much, let's call that 7%. So we'll call that 0.07. And now we're ready to build our confidence interval. So every confidence interval is made the same way. We start with our point estimate. And then we have to add and subtract the margin of error. And the margin of error, because this is a 90% confidence interval, it's made by using 1.645 of my standard errors. This is the critical value times the standard error. So my critical value is 1.645, and the standard error is 0.07. And I can use that to calculate my lower boundary and my upper boundary. So let's do that on the calculator. So 0.46, I will subtract my critical value, 1.645, times the 0.07. So we're going to call that, let's call that 0.345. So that will be the lower boundary. And for the upper boundary, we'll take the 0.46 and we will add 1.645 times the standard error. And that gives me an upper boundary of, we'll call that 0.575. And in this way, we've built our 90% confidence interval. So all we need to do then is interpret this confidence interval. So we are 90% confident So start by indicating the accuracy level of the method that you're using. So we're 90% confident that the proportion of red beads in the class bead bag population. So after you've stated the accuracy level of your method, you should always state what type of a parameter you're trying to capture. This is about a proportion. And then you should describe what that proportion is in context. It's the proportion of red beads in the class bead bag population. So we believe that it's between, so is between 0.345 and 0.575. And in that way, we've interpreted the confidence interval. So that interpretation allows us to make decisions. So for instance, does this confidence interval give us evidence that the real population parameter is below 60%? Does this give us evidence that the actual percentage of red beads in the bead bag is less than 60%? The answer is yes, because no matter where the truth may be in this confidence interval, every possible value for the population parameter in this interval is below 60%. So same thing, does this confidence interval give us evidence that the true parameter, the true percentage of red beads is higher than 30%? And the answer would be yes, because 30% is well below the lower boundary of this interval. In other words, you could also say that every possible value for the population proportion in this interval, every possible value is above 30%. So notice what the interval can't say. So for instance, do I have evidence that the population proportion, do I have evidence that the percentage of red beads is higher than 50%? Well, notice 50% is in this confidence interval, but so are lots of other possible values. So I do have values like 51%, 52, 56.83 repeating percent. I have plenty of possible options in this confidence interval that are higher than 50%. But I also have plenty of options in this confidence interval that are lower than 50%, 41%, 38.264%. So this confidence interval would not give us evidence that the true parameter in the population bead bag, it does not give us evidence that the true percentage of red beads is higher than 50%. Of course, we do happen to know the truth. In our bead bag, the truth is 40%. So this confidence interval does happen to be one of the confidence intervals that captures the real population parameter. Just something important to review or reiterate. This 90% is not the probability that we have captured the population parameter in this interval. That 90% tells us the accuracy level of the method. If we built many, many confidence intervals using samples of size 50 from this same population, using exactly the same method repeatedly many, many times, about 90% of all of the intervals that we could construct would capture the real population proportion. So when all we've done is take one random sample and build one confidence interval, either the truth has or the truth has not been captured within this confidence interval. So just important to remember that 90% is not a probability that we've captured the real parameter in this interval. So before we wrap up, let's just look at a couple of other things. There are other standard levels of confidence and z-scores or critical values that it might be good to know, and frankly, I would memorize these. So the other confidence levels that I think are important to know are 95% confidence and 99% confidence. So let's just practice using the inverse norm command to find those. So for 95% confidence, what that means is that we have cut 5% off of the tails of the distribution, but that's 2.5% on each side of the distribution. So 95%, that means I've cut off a total of 5%, but on each side of the distribution, half of that is 2.5%. That 0.025 is what you want to put into the inverse norm command in order to find the critical value. So the inverse norm command accepts percentiles. So this 0.025 can be considered the lower percentile so that we can find our boundary. So that critical value would be 1.96. So, and we know that approximately 95% of normally distributed data would be within 2 standard deviations above and below the mean. We're just being a little bit more specific with this critical value here. So to find for a confidence level of 99%, that means that we've cut 1% of the distribution. We've cut off the highest and lowest 1% of the distribution, but I want to find just the part that's on the left side. I want to find just this part so that I can interpret it as a percentile and I can use the inverse norm command. So that's why we have to take this 1% and we have to cut it in half. So it's really only 0.5% that we've cut off of the left side. That's what we will put into the inverse norm command to find the critical value for 99% confidence. So be careful, don't put in 0.5. It is 0.5%. As a decimal, that's 0.005. So this time, to get 99% confidence, we need a much larger critical value. Our critical value, we'll call that 2.58. So notice as the level of confidence increases, the confidence interval is going to get wider because the critical value is getting larger. So for 95% confidence, we have to use 1.96 standard errors above and below the point estimate. For 99% confidence, we have to use 2.58 standard errors above and below the point estimate in order to build our confidence interval. Of course, don't forget, you can make the confidence interval then narrower by lowering the standard error, and you can get a smaller standard error by using a larger sample size.